God bless you all. In the last video, we saw that why do we use SI units? In that point, we stopped that video. Okay, today we will continue with the definition of basic SI units. So before understand the definition of the basic SI units, so we should, it is better to understand why should we have a definition. Actually, the first reason is the clarity of meaning helps us understand exactly what a word, concept, or idea means. So without a clear definition, people might interpret things in different ways, leading to confusion or miscommunication. For an example, if you take a word organic, so let's say organic, if I take a word organic, without a clear definition, what will happen? One person might think the organic means it's natural and healthy. Another one might think it's just means no chemicals. Someone think about the natural and healthy, and someone think about, oh, it is organic means it's no chemicals. A farmer might say it means ground paddy or ground agriculture product ground without synthetic pesticides or fertilizers. Might say like that. And the marketer might use organic to sell products that are not strictly regulated. So there are confusions, and if without a definition, there are confusions for a word. For an example, if you take an organic, so there are many interpretations or many opinions having different people. So that's why, with a clear definition, we can say the organic in agriculture, food produced without the use of synthetic pesticides, genetically modified organisms, or artificial fertilizers, and certified by a regulatory authority. So this is one the definition of organic in agriculture. So now everyone can organic. It clears up misunderstanding and allows for accurate discussion and decision making. So whether you are a consumer or farmer or scientist or policymaker, so everyone can use a same definition. The second one is, why should we have a definition? Shared understanding. What do you mean shared understanding? In any discussion, academic or professional or casual, having a definition ensures that everyone is on the same page. It sets the boundaries for what we are talking about. For example, in everyday conversation, the people often use distance and the displacement. Distance and displacement. So people are using the words distance and displacement, but people are thinking both are the same. Distance and the displacements are same. But the definition, those are vary. In physics, the terms have the distinct definitions. You may know as a physics student, distance, the distance means, the definition of the distance is the total length of the path traveled by an object regardless of direction. Regardless of direction, it's a scalar quantity, meaning it has only magnitude and the no direction. So the distance is total length of the traveled by an object. Total length of the path traveled by an object. That is distance. But displacement, the straight line, straight lines distance from the starting point to the end point. That is the shortest distance. Shortest distance of an object traveled. So that is called displacement along with the direction. Along with the direction. It's a vector quantity, meaning it has both magnitude and direction. So while we are talking, or while we in the conversation, we may talk about the distance and displacement, the meaning of similar type, but in the physics or by the definition, there is a different distinct definitions in the if you take in the definition. So that's why the shared understanding should be given by the definitions. Okay, let's say third one is precision in thinking. So why we should have a definition? It will give a precision in thinking. Precision in thinking. So definition help us think more precisely. In science, law, philosophy, and even daily life, clear definitions make it easier to reason, analyze, and make decisions. Let's say a context, a group of students is doing an experiment to observe how substances heat up when energy is added. A group of students is doing an experiment to observe how substances heat up when energy is added. So without the definition of this context or this experiment, one student says the metal has more heat than water because it feels hot. They heat a metal, it heats immediately, and the metal has more heat than water because it feels hotter. Another replies, but the water has been on the burner longer, so it must have more heat. It's a problem now. So there is a without the definition or without the understanding of the definition of heat and temperature, the students are having different opinion and interpretation. So what is here? The confusion happens because they are mixing up heat and temperature. Terms that feel similar but mean very different things in physics. With clear definitions, heat means the energy transferred between two systems or a system and its surroundings due to temperature difference. It's measured in joules. So that is the definition of heat. You take a temperature, a measure of the average kinetic energy, of the particles in a substance. It's measured in degrees Celsius. If you give a temperature, if a particular objects increasing the temperature means the molecules absorbing the energy. Because of that, the kinetic energy increases. So the temperature means a measure of the average kinetic energy of the particles in the substance. It's measured in the degrees of Celsius. So now the students can understand the metal may have a higher temperature. The metal may have a higher temperature, meaning its particles are moving faster on average. Because of that, the metal have a higher temperature. But the water, because of its larger mass, it may contain more heat energy overall, even if it feels cooler. If you keep the water in the burner long time, because of the heat capacity, it has heat energy more because of its mass. So even it is cooler, it has more heat energy. But the temperature of the Metal is high because of the particles are moving faster on average. So that context, the experiment, because of the definition, the students can have clear understand. So that's why we should have a definition for precision in thinking in an experiments or discussions and researches and other areas. Okay. In that sense, we will see that the definition of SI units, the definition of SI units, the basic SI units, sorry, the definition of basic SI units. Let's say a meter. So meter means it has a definition. It has a definition. We cannot say meter, it's meter, but meter has, what is meter? So meter is the length of 1,650,763.73 wavelengths of radiation emitted in a vacuum due to the transfer of an electron between energy level 2p10 and the 5d5 of the krypton 86 atom. You will discuss, you will learn in the physics or in the chemistry, as well as in some areas will be outlined in the physics. The atom, each an atom having a different energy levels. So S energy level, P sub energy levels are like that. So from in the krypton atom, from 2p10 and 5d5, between the energy level of 2p10 and 5d5, if an electron transfer in a vacuum, that radiation wavelengths of 1,650,000 into 763.73 wavelengths, length of the wavelengths is 1 meter. That is the definition of the meter. Definition of a meter. So, historical note, this method is defining the meter was replaced in 1983. In the resource books, it is mentioned the meter definition is the wavelengths, that means 1,650,763.73 wavelengths of radiation emitted in a vacuum due to transfer of electron between the two energy levels, that is from 2p10 to 5d, in between 2p10 and 5d5 of the krypton 86 atom is the given definition in the resource books. But the historical note is this method of defining the meter was replaced in 1983 by a more accurate and a universal definition. The meter is the distance light traveled in a vacuum in 1 over 299,792 and 458 of a second. 1 over this much, almost 300 million second. 1 over 300 million second. In a second, in 1 over 300 million second, what is the distance of light traveled? It's called meter. That is the definition of basic SI units definition. Let's say the definition of second. Second is the time required for 9,192 million, almost 9,192 million periods. Periods means one phase, equal phases, no? Equal phases, okay, 9,192,631. Sorry, 9,192,000 million and 631,770 periods of radiation due to the transfer between two micro level in the ground state of a cesium 133 atom. The micro level of ground, micro ground state of cesium. So atomic, around the atomic, there are subcells and what do you call micro level of energy levels in the ground state. So what they are telling, the second is the time required for 9,000, for example, 9,192 million periods of a radiation due to the transfer between the two micro levels in the ground state. That is the second. That is the meaning of second. This is a very precise measurement, which is why atomic clocks are used globally to measure the time based on this definition. This standard ensures that time is measured accurately and consistently across the world. Okay, so we saw that meet the definition of meter and second. The third one is ampere. Let's say ampere is the current that exists in each of two infinitely long parallel straight wires with negligible circular cross section. So it means that much thin. The thickness is negligible. That means okay, the cross section is negligible. Placed 1 meter apart in a vacuum, which results in a force of exactly of 1 meter length of each conductor. So in the, you can see that the figure, the ampere, actually the ampere is defined based on the magnetic force between two electric currents. So the ampere is defined based on the magnetic force between two electric currents. So actually the 1 ampere is the amount of current that when flowing through two infinitely long straight parallel conductors placed 1 meter apart in a vacuum produces a force of exactly 2 into 10 to the power minus 7 newtons per meter of length between the wires. But they are telling two infinitely straight lines having the current. Okay, what is the force exactly? What is the force produced? That is magnetic force produced 2 into 10 to the power minus 7 newtons of 1 meter length per meter, and it is kept apparent 1 meter of two parallel straight wires in a vacuum. It produces the magnetic forces. It's 2 into 10 to the power minus 7 newtons. The amount of current that produce that much of 2 into 10 to the power minus 7 newtons of magnetic force. It's the definition of ampere. So the ampere is the amount of current that when flowing through two infinitely long, okay, straight parallel conductors placed 1 meter apart in a vacuum, that current produces a force of exactly 2 into 10 to the power minus 7 newtons per meter of length between the wires. Per meter length between the wires. Okay. So according to the right hand grip rule, so you can see the forces are produced by the current. So this forces the magnitudes of 1 meter. In a 1 meter, it produces 2 into 10 to the power minus 7 newtons. That amount of current is called 1 ampere. So the ampere definition is clear. What is Kelvin? The Kelvin is the thermodynamic unit of a temperature. So the Kelvin is the fraction of 1 over 273.16 of the thermodynamic temperature at a triple point of water. In the heat, you will study further. So, okay, just I will brief what is triple point of water is the specific temperature and the pressure at which water can exist in all three phases. That means the water is in solid phase, liquid, and the gas all are in a simultaneously in equilibrium in one temperature and the pressure at which water can exist in all three phases. So that temperature is exactly 273.16 Kelvin. So the 1 Kelvin is 1 over 273.16 temperature of that temperature. So this was the previous definition of Kelvin. But from May 2019, the new definition is based on the Boltzmann constant. Boltzmann constant, making it independent of any particular substance like water. So once Kelvin is defined by mixing numerical value of the Boltzmann constant to be exactly 1.380649 into 10 to the power minus 23 joules per Kelvin. So, okay. So we will see later what is the Boltzmann constant and all. So for example, now you can remind this is the Kelvin thermodynamic unit of temperature. Kelvin is the fraction of 1 over 273.16 of the thermodynamic temperature at a triple point of water. That is the definition of the Kelvin. Okay. The next one is candela, that is CD. Candela is the luminous intensity that is produced perpendicular to a surface of 1 over 600,000 square meter of black body. 1 over 600,000 square meter of a black body at a temperature of freezing platinum under a pressure of 101,325 newtons per meter. So candela is the luminous intensity that is produced perpendicular to a surface of 101 over 600,000 square meter of a black body at a temperature of freezing platinum under a pressure of 101,325 newtons per meter. That is the definition of candela.